Hello, everyone. This is a second lecture on section 7.2 on applications of exponential functions. Um, so last time we looked at several examples of using exponential functions to model real-world situations. Um, One of those was compound interest, and we use this formula for compound interest. And again, here the P is the initial amount, how much you have at time 0. Okay. T is going to be the time in years. 100R is the percent growth rate. R will usually be given as a decimal. So 100R is the percent. So if you have a 5% rate, R is 0.05. Okay? And then N is the number of compounding periods per year. If you are compounding monthly, which is what most savings accounts do, N is 12. If you're compounding yearly, N would just be 1. Okay? So this exponential function is the type of function you would use if the amount that's being added, the interest in this case, comes at fixed intervals every month, every 3 months, every year. Okay? Um, there's also what we call continuous compounding. And this gives us a slightly different type of equation. Here, A of t will be P e to the RT. Okay? The P and the T mean the same thing as before. P is your initial amount, how much you are investing, if you think of it that way, and T is the time in years. The R will be also the same. It's telling you what the interest rate is. The E is a special number. Okay? E is approximately 2.71828. Okay? We just use the symbol E just so we don't have to keep writing out 2.71828. It's just like we use pi is 3.14 for area of circles and things like that. It's just a symbol we use as a shorthand. Okay? Your calculator, including your iPad calculator, will have an e to the x button. And so when you're doing problems that involve E, you'll use that button to do the calculation. Okay? So let's say, oh, and I guess we should say what we mean by continuous compounding here is that rather than the interest or increase coming at fixed intervals, it happens continuously over time, every minute, every second, etc., etc. I guess if you want to make an analogy, annual interest means you get paid your interest once a year. And populations, some populations, some types of species work the same way. As I understand, cows reproduce generally once per year. That would be annual compounding. People do not reproduce once per year. People are reproducing all the time, every minute, every second. So that would be continuous compounding. So you can think of that as the difference. Okay. So we can use this formula for money. So let's do an example with that. Last time we looked at investing $1,000 at a 10% rate for 1 year. Okay? At annual compounding, we ended up with $1,100 after 1 year. At quarterly compounding, we had, I think, an extra $3.80, $1,103.80. Let's see what happens with continuous compounding. So how much with continuous compounding? All right. So we want to do a of 1. Well, we'll use a of t. Our equation is going to be 1,000 e to the 0.1 times t. Okay. If t is 1, a of 1 is just going to be 1,000 e to the 0.1 times 1. Okay. If we use an e to the x button on a calculator, we'll get e to the 0.1 as 1.10517. All right, so then we're going to end up with $1,105.17. Okay, so we get an extra $5.17, not a big deal, with continuous compounding versus if we did annual compounding. All right, now we use this type of equation a lot for population modeling. Again, most species, people, bacteria, viruses are going to grow continuously, not at fixed intervals. Okay, so let's say we have a city currently has, let's just, as a nice round number, 100,000. Okay, and let's suppose the population growth rate is 2%. R is 0.02. Okay. Let's use P of t is, let's erase this here. 100,000 e to the 0.02 t to model the population. Okay. The 100,000 again is representing the starting current population at time 0, and the 0.02 in the exponent, that's representing a percent growth rate. Okay, we could use this to find the population at any particular point in time. So let's say in 20 years, the population would be we would just go P of 20, it's 100,000 e to the 0.02 times 20. Okay. When you're doing this on your calculator, you do want to make sure to, you will probably want to calculate that first before you use your e to the x. So 20 times 0.02 times 20 will be 0.4, and then use your e to the x button to get that value there. I'm just going to wander over to my calculator here. 0.4 e to the x. So we're going to get 100,000, and that's about 1.4918. Okay, rounding a little bit. So that's going to be 149,180 or so. Okay. All right. Now let's do one other example. And we'll go back to percentage. Okay, let's say we want to look at n of t is number of COVID coronavirus cases in the U.S. At time t. Okay, and let's say I think today the number of cases in the U.S. Is about 32,000 total cases. Okay, so 32,000 now. Okay. Now, one feature of exponential functions, they grow at a fixed percentage growth rate, which also means they grow by multiples. Okay, and while we won't look at the actual data for this, right now, COVID cases, every 8 days, we have about 10 times as many cases. That's been happening now for a couple of weeks. Okay, so we can use that information to find the equation for n of t. Okay, we're going to use n of t is, we have 32,000 now. Okay, we don't know the r at this point, and we're going to measure t not in years, number of days from now. Oops, make that a now. Okay. Now, every 8 days, we're having about 10 times as many cases. So what does that mean? That means n of 8 should be 320,000, 10 times what it is now. Okay. If we use that together with an exponential growth equation, okay, we could set that up this way. The 320,000, that's how much we're going to have in 8 days. That's going to be the 32,000 times 1 plus r to the 8th. Okay. We can solve this for r, and that would tell us the whole equation. Let's divide both sides by 32,000. So 10 is going to be 1 plus r to the 8th. Okay. How do we undo 8th powers? We use 8th roots. Okay. So you can do this on your calculator. We want the 8th root of 10. Okay. The 8th root of 10 is going to be 1 plus r. Okay. On our calculator, the 8th root of 10 is about 1.231, so that's 1 plus r. All right, so that means r is 0.231. Okay, what does that mean? If you think of that as a percent, COVID cases are increasing 23.1% per day because we were measuring time in days. All right, so yes, this math is a little bit of an indication why we're all staying at home. Not a lot of people are sick now compared to the whole population, but if this trend continues, if we continue to have 23% per day, more cases, we are going to have a great many cases before too long. So that's it for this lecture. The next lecture will be on 7.3. We'll be getting into logarithms.